Okay, so section 10.5 is on the number e. So I've kind of mentioned that there is a number e. It's kind of like pi. It's called a transcendental number where it goes on forever. It never repeats. Yes? No. So I do not have one. You can just look at people's next to you. All right, so basically if you hit e on your calculator, there's a couple different places you can find it on the calculator. So it's on the left side with e to the x. So you could do e to the 1. And it looks like it falls into a pattern. So the calculator tells you it's 2.718281828, but it doesn't. It doesn't have a pattern. That's all right. So it says in section 10.1, we talked about using the formula a of t equals p times 1 plus r to the t when determining our interest. Okay, we're going to make that formula a little bit different. Okay, that's not really what banks and so on use for their formula. So p is the initial amount, r was the rate, and t was the number of times we compounded. But when you actually go to the bank, it's not, like I was saying, it's not how it works. Okay, so let's say you have $100, and you go to the bank and it says that it has a 3% interest compounded monthly. You would think that after 1 month, if you added 3% interest from $100, how much would you think you have at the end of the month? $103, right? That's not actually what happens. Okay, so when you say something like compounded monthly, it actually will affect the rate too. It takes that rate that you had, the 3%, and it divides it into 12 pieces. And that's the amount that you're getting at the end of the month. So it's very misleading, isn't it? It's like, wait a second, I thought I was supposed to get 3% at the end of the month. You don't actually get 3% at the end of the month. You divide that rate by 12. So this is what the formula looks like. So it's going to be p times 1 plus, instead of just having r, we do r divided by n. R divided by the number of months or number of times it's compounded each year. But then when we raise it to the power, we don't just raise it to, you know, if I said find the amount after 4 years, we don't raise it to 4, we would actually raise it to 48, okay, because it's compounding 48 times in those 4 years, if it's every month. Okay, so it divides the rate, but then it gives you more times compounded. So it's a little confusing, but let's try some examples. So it says determine the amount that a $10,000 investment is worth in 4 years if it has an interest rate of 8% and is compounded annually and quarterly. Okay, so annually, if we talk about that, our number of times it's compounding each year is just at the end of every year, right? So it's going to be n equals 1. But quarterly, the number of times it's compounded each year is going to use an n value of 4, right? 4 quarters, 4 times a year. So our p value is that $10,000. Our r value is 0.08. That's how we write 8%, right? 0.08. Okay, so we're going to have our amount after 4 years, so t is equal to 4, is going to be our initial amount, which was $10,000, times 1 plus our rate is 0.08, and we divide by the number of times we're compounding, which is 1 in this case, and we raise it to the 1 times 4. This is for the, in 4 years, compounded 1 time a year. But, okay, so 1 times 4. All right, so we find that. So typically I kind of find what's inside the parenthesis first, but your calculators can actually handle all of that all at once if you have a graphing calculator. So you could put in 10,000, so go ahead and try it along with me. 1 plus 0.08 divided by 1, which you don't really need to divide by 1, and then raised to the 1 times 4. The only thing I caution you with is when it's not even when it's 1 times 4, you actually are going to need parentheses there. So if you don't do that multiplication first and just say in your head, oh, it's 4, then put parentheses around that power. Okay. I would just do the multiplication in your head and be like, oh, it's going to be 4. Okay, so that means after 4 years, this $10,000 investment is $13,604.89. It should always make sense in the end. I don't know how many times I have Algebra 2 students who mess up the rate, and instead of putting in 0.08, what do you think they mess up on? What do you think they put in instead of 0.08? They put in 8.
But then they'd be a millionaire.
If you put in 8, your answer is 6561000, and you've made $65 million in 4 years by investing $1,000. Think about your answers, please. Please think about your answers because it doesn't make any sense, right? It's like those ones we talked about with the job sharing where it's like, oh, this person works with the other person, and then it takes them longer to do the job. That doesn't make any sense, right? So think about it. All right, so that's our answer. So let's do the same thing on this next one. So if we're compounding quarterly, that means instead of having that 0.08, the bank is tricky, and they don't give you 8% at the end of every month. They're actually giving you only 2%, right? They're taking that 0.08 and they're dividing by 4. But then they're compounding it more often than just after every single year. They're compounding it 4 times a year, or not, yeah, 4 times quarterly, right? For 4 years. So how many total times are we compounding? 16. So what goes up here is 4 times 4. Now that's the part that I would go ahead and find before doing that. I put a little star there. The dot gets a little confusing. So it's going to be 4 times 4, which is 16. So 16. Because we're still going for 4 years. So 4 years compounded 4 times a year.
So it's still 8 times 4 at the beginning. 8 times 4 equals?
Yeah, the amount equals the P. So yeah, the A, it's not A times 4 technically, it's A of 4.
Oh.
That's how we read that, kind of like a function f of x. So we read that, the amount after 4 years. So never divide by 4 or anything here. A lot of students will try to do that. Okay, so let's find what this is. So we're going to put it all in. You should get just a little bit more than that other answer. So 13,727.86. Did you guys get that? Why do you think I'm rounding to 2 decimals? I usually round to 3. Because it's money, right? It makes sense. Only gas stations use 3 decimals for money. Have you seen that, gas stations? Isn't that annoying?
I don't think they would round up. They'd round down.
Mm-hmm. Yeah, they'll get every penny from you, won't they? All right, does this make sense? They're pretty close. They're not going to be like really, really different, okay? But you would think the more times you're compounding each year, the better. So let's see. So if I do monthly and daily, how does that affect it? So monthly means our amount after 4 years is going to be our $10,000, 1 plus the 0.08, divided by what now? 12, because it's monthly, raised to the 4 times 12. So I would just do that in your head and say, okay, that's 48, and then raise it to the 48. Now you can use a button on your calculator which helps you pull up that last thing you did so you can just edit it. Some of you guys, do you guys have the calculators where you can go up and grab those? Yeah, so you could go up and grab the equation, or you can do second entry, which is second enter, and it pulls up the last thing you did. So you can edit it, and I got $13,756.66. So previously we had 727 at the end. Now we have 756. So we're getting a little bit bigger. So daily, you would think, oh man, it's daily. That's going to be a lot more, right? But every time that we're compounding it more often, like we're doing 4 times 365, which is a really big exponent, what else are we adjusting? That rate, right? We're dividing it. So it's kind of like offsetting those two things. It is more, but it's not like drastically more like you would expect. Did you guys get that? So $13,770.79. Okay, so it says if we kept going, one would think that your $10,000 investment would grow really, really large, because it's like, well, what if we compound every single second or every single nanosecond? Or you would think it'd be huge, right? But it's kind of following that same thing where we're dividing by the rate as well. So there's kind of a limit to how big it's getting. It's limited by that. So it says, suppose we start with $1. So let's kind of see what this limit is. So instead of $10,000, let's talk about how much every single one of those dollars is growing. So let's say I have $1. And I'm going to do, instead of 8%, I'm going to do 100%. So let's say I have 100% growth. Then I'm going to use this $1 times 1 plus 100% growth divided by n raised to the n times t. That's the formula I'm using. So let's figure out for 1 year how long it grows. So instead of t being I'm going to figure out for 1 year how long or how much that $1 is growing to. Okay, so let's find all of these numbers, and we'll find them pretty quickly. So if I'm finding it annually, then I have my $1. I take my 100% rate. I'm dividing by 1 time a year and raising it to the 1. So Eric, what is that number? I bet you know. It's, oh, not 1. It's 2, because 1 plus 1, right? So it's 2. So the next one's a little bit harder to do on our head, so let's use our calculator. So I have 1 plus 1 divided by 4, raise to the 4. That $1 is growing even more. It's growing to $2.44. So I'm going to write 2.4414. Well, what if I did monthly? Then I would plug in 12 for my n. Forgot a parenthesis. It told me 1. That doesn't make sense. And in that case, so 1 plus 1 over 12 to the 12, it's growing to 2.6130. Do you see how it's getting a little bit bigger every single time? So daily, we would divide by 365 and raise to the 365. Need me to get that one? 2.71457, somewhere around there. And then every minute, do you guys know the song that involves 525, 600? Do you guys know that song? It's always in my head when I hear this. 525,600 minutes. Yeah. That's how many minutes are in a year. Or moments in a year, as they say. So I get 2.718279215. So if we kept going, if we found every second, every millisecond, and so on, so every single moment, so we would say like compounded continuously, compounded every single split second, I guess, then this number would be E. Okay, that's where E comes from. Do you guys see it? So E is the number 2.718281828. It doesn't repeat like that, though. It looks like it repeats. I should find more decimals there. So this is called the natural number. So E is the natural number. So when we have log base E of a number, that is called natural log because it's using the natural, whoops, not natural log of E, natural log of X. So log base E is the same as natural log of X. This is where people are always like, well, why isn't it in L? Okay, do you guys remember how we started talking about like John Napier? John Napier from the article. He's French. Napier is a French name. A lot of mathematicians did. He's not actually French though. A lot of mathematicians did their work in France. So how do we say things in French when we talk about an adjective? Like if I said the red car, it's car red, right? So that's why it's log natural. Does that make sense? So it's ln instead of nl. Are we good? Do you guys get that? So anytime you see ln, just write log base E. All the rules for logarithms still apply. So it says when things are compounded continuously, so we don't end up using that formula, that p times 1 plus r over n to the nt. We use another formula. I don't know if you guys have seen it. It looks like a, or a of t, equals p e raised to the r times t. So it's the Pert formula. Back in the 80s, there was a special shampoo called Pert Plus. Have you guys heard of Pert Plus? My husband still uses it. No one has ever heard of it. My husband still has to have his Pert Plus. It's hard to find. It is very, very hard to find. It's in a green bottle. It smells like Vicks Vapor Rub. Do you guys know what that is? Wakes him up in the morning. I don't know. So it's really gross. All right, so who knows? All right, so it says, no, if something's growing, the rate is positive. If something's decaying, the rate is negative. So if you have, like, R is a negative number, it means that it's going to decay. But if the R value is a positive number, it means it's going to grow. Okay, so examples. So remember, natural log is really log base E. I don't know why we do this to Algebra 2 students. We should just write log base E. Because when I write this, log base E of e to the 0.15t, immediately people know what the answer is. Okay, think about it. Do you guys remember when we had like log base 8 of 8 to the 5? Do you know what it was? It was 5 because the log base 8 and the 8 cancel. So here, log base e of e to the 0.15t, what do we think it is? That 0.15t, that's it. Because what's happening is that is going to the front, and when you have log base e of e, you're saying, what power do I raise e to in order to get e to the 1, right? Log base e of e is 1. So in other words, when you see natural log and e next to each other, they cancel. Goes away, right? Natural log and e makes 1. Okay, so if I see something like this, I have e to the 3 times natural log of x plus 1. They're not quite next to each other. If I had e, so if I had e to the log base e of 7, I could say, oh, that's going to be 7. So in other words, e to the natural log of 7 is going to be 7. Okay, but we don't have that quite. We have this tricky little 3 there. So what we're going to do with that 3 is we're going to pull it back up as a power. So it's going to look like e to the natural log of x plus 1 to the 3. So once we do that, what can we say our answer is? Yeah, close, not 3x plus 1, but x plus 1 raised to the 3. Yep. So x plus 1 to the 3, like that. Does that make sense? Do you guys see how the e and the natural log cancel each other out? It's kind of the same rules that we've talked before about logarithms. Okay, so this next one I could do in 2 different ways. We first see that we have 2 logs that are added together. So if we have 2 logs that have a plus between them, if we wanted to combine them, we would combine them with addition, right? Or not addition. If we have addition, we would combine them with multiplication. So we could say, I'm going to do both ways here. So we could say that this is going to be natural log of e to the 2x times e to the x. So let's think about that. E to the 2x times e to the x. Think about our exponent rules. If I had x to the 5th times x to the 8th, it would be x to the 13th, right? You'd add those powers. So what are we going to get here? E to the 3x, right? So it's going to be equals natural log of e to the 3x. So what is this all going to equal? 3x. Do you see it? Okay, personally, I think that way was harder. Yeah, so what are you saying?
So you start 2x times.
Yeah, so he's saying, why don't we just cancel here at the beginning and say that's 2x, and cancel here and say that's x, 2x plus x is equal to 3x. Wouldn't that be much easier if we had recognized that from the beginning? So remember, there's lots of ways to do logarithms. So don't get upset if maybe you did the problem a different way than someone else. Okay, so let's try this. So Brian invests $500 at a 5.25% interest rate compounded continuously. So this is not saying monthly, daily, every second, or anything like that. It's saying constantly, continuously. So every single time you see continuously, it is a different equation than that a of t equals p times 1 plus r over n. It's not that equation. Which equation was it? This one. A equals p e to the rt, Pert. So we're going to use that equation. So it says, how much does he have in 40 years? We're going to say our amount after 40 years is equal to our initial amount, which was $500, the amount we put in. That's how I remember P, put in. It's called the principal amount. And then I have my E raised to the R, so I have 0.0525. Does that make sense? 5.25%. I moved the decimal place over twice. Times T, which is 40, so I'm going to do that little asterisk there, times 40. So just make sure that if you have a calculator that doesn't do the fancy font and doesn't raise it up, you put a parenthesis there. So check to see that you get the same thing. Now this one is pretty different than $500, but why is this so much more? How many years did he have it invested? 40 years. Yeah. So he's not making really that much in 40 years. And in pre-calc, you really do the real type of things that banks do. Because, you know, like investment accounts, like if I have a 401k. You guys know what a 401k is, right? Like a retirement account. Do you think that I probably just put in like a lump sum of like $1,000 and just wait?
No.
What do I probably really do?
Part of your salary.
I take out part of my salary we get our salary twice a month. So every couple weeks I have a payment, like the 15th and the 30th. I take my money from my account and I put in like $200 or something into my retirement account. Okay, so how's that different than what we're doing today? These are just like putting in a certain amount and just waiting. Is that how bank accounts really work? Do we just like put in a certain amount of money when we're like 17 years old and say, oh, I guess I'll retire when I'm 65? No, we don't do that, right? We really like continuously invest in our account. So in pre-calc, we do another equation, which is a little bit more complicated. Yeah.
So would that mean that, like, as you put in more money, so I have a job right now. I have a savings account.
Uh-huh.
I'm putting money in my savings account. And is there interest on that? And
Yeah,
does it,
totally.
as the money in my bank account gets more, does the interest
Uh-huh.
go as well?
The interest doesn't go up as well, but the principal amount. So it's like every single month you have a different principal amount then.
The interest rates are much lower because compared in savings accounts, which is why now I have a brokerage account because you can invest in stocks instead of having in my savings account. I think I get 0.01% interest from Chase.
Yeah. So yeah, you get different. Yeah.
And you're actually losing money to inflation.
Yeah, that's very true. Very true. Do you guys see what he's saying? So he's like, investing in banks maybe isn't the best way because sometimes you get a different, not a good percentage rate compared to investing in stocks and so on. But stocks are much riskier, right? So
That's why you always
Or ETF.
you use a combination. So like it depends on how old you are. We'll talk about all this. This is a great conversation. All right. So if I have e to the 3x minus 4 equals 10. So let's try to solve some equations. So e to the 3x minus 4 equals 10. What do you think we do first? Add the 4 over. So I get e to the 3x equals 14. And I'm going to take the natural log of both sides because I want to get rid of that e somehow. And I want to somehow drop the 3x. Okay, so you could switch forms. Do you guys remember how we switched forms? So if I switch the form, I would have log base e of 14 equals 3x. Right, that's how I would switch forms. But what was log base e? ln. So that is natural log of 14 equals 3x. Let me show you the trick here. So if I go to this original equation, this e to 3x minus or equals 14, and I take the natural log of both sides, do you guys see how we get 3x equals natural log of 14? Isn't that the same thing? So don't sweat like trying to remember how to switch those forms. The easiest thing if you have e is just to take the natural log of both sides. So we're going to be doing that. Take the natural log of both sides. So now we divide by 3. So we have x equals whatever natural log of 14 is, all divided by 3. So we find it. Natural log of 14. Oops. Do you guys see the natural log button on your calculator? So I get 0.8. We'll do 880, 3 decimals. I always have you guys do 3 decimals on the test. All right, so this next one, I'm going to add the 2 over, so I get 36. I'm going to divide by 6, so I have e to the x plus 5 equals 6. I'm going to take the natural log of both sides. That natural log and e are going to go away, so I'm going to be left with x plus 5. It's not just hanging off in the air, though. Do you guys see how we're canceling? But what's really happening is this x plus 5 is the power, which is going to the front because of the logarithms. Yeah, Anna Catherine. I just did it on both sides. I didn't switch forms. You can switch forms if you want, but I just did it on both sides, so that goes away. So you can kind of cross that out. So then I have natural log of 6. So then my answer is going to be x equals whatever natural log of 6 is, and then minus 5. That's not natural log of 1. Do you guys see how natural log of 6 goes together? So we find natural log of 6, end your parenthesis, and then subtract the 5. So you should get negative 3.208. I liked the What's that? Okay, so that's why I have you guys using your calculators and checking. Make sure you're getting the same thing. Sorry. We good?
That song stuff.
I know. Every year, 525,600 minutes. Yep.
About that problem.
Mhm.
So anytime the natural lie, there was an E, and then you said on both sides. So you can get like what?
It's not on both sides. The natural log and e cancel.
Oh, okay.
Yeah, do you see it?
Yeah.
But really, like this natural log is log base e. Oops, log base e of 6, like that. So there is kind of an e that's there. It's just invisible. Okay, next one. So now let's switch from logarithmic form to exponential form. Can we do this? This is where students do not like this because they just don't see it. They're like, I don't see what my base is. I don't understand how to do this. So if you don't see the base, remember, that is log base e. Put a little e in there. And then think, well, now how do I switch forms? You see it? Yeah, so it's e to the 3 equals 5w minus 2. So e to the 3, I know it looks like x cubed or something. E to the 3 is a number. So our answer is going to be e cubed added to 2. And then if I have 5w, I divide by 5 to get my w. So that would be the exact form of the answer. So let's find what that is. I'm going to find e cubed. I'm going to do plus 2. I would probably hit enter now, and then take that result and divide by 5. So that way you don't have to put parentheses in. If you put it in all together, you'll need parentheses right there with the e cubed plus 2. So you should get 4.417 equals w. Okay, making sense? Okay, we're going to add the 3. So I have 2 natural log of 6y plus 7 equals 14. I divide by 2. So natural log of 6y plus 7 equals 7. And now I'm going to switch forms. So if you don't see it, rewrite natural log as log base e. Sometimes I'm kind of lazy and I just kind of sneak an e in there, although that's kind of bad notation, natural log base e. It's really log base e, right? And then I switch forms. So I do e to the 7 equals 6y plus 7. So I find that e to the 7. I subtract 7, and I divide by 6 to get my answer. Do you guys see my steps? So subtract the 7 over, divide by 6. So e to the 7 minus 7 divided by 6. 181 something. Did you guys get that? So 181.606. Is that it? Is that the last problem? Oh, half-life, okay. Okay, so the last thing we have to talk about is half-life. Did you guys ever talk about half-life in like chemistry class and so on? Have you guys done that? Okay. So half-life is how long it takes for half of something to decay. So we find the age of like fossils and so on with something called carbon-14 dating. It's very similar to that. So we were talking about carbon-14 dating the other day. Like carbon changes into a different form for something that's alive and something that's dead. So a half-life, let's say I start out with 1,000 milligrams of some object. And let's say my half-life is every 7 years. When will I have 500 milligrams? After 7 years. So when will I have 250 milligrams? After 14 years, after another 7 years. Does that make sense? When will I have 125? After 21 years. That's how a half-life works. Does it make sense? Am I going to get to 0? No. Not really. You're just getting closer and closer and closer to 0. Does it make sense? Okay, so that's what a half-life is. So it's the amount of time it takes for half of a substance to decay. So you could know this formula, and some people memorize it for the test. Okay, you don't have to know that formula. I'm going to show you how to do it without memorizing that. So it says plutonium-239 has a half-life of 24,110 years. So that's our half-life, H. So how long does it take for a 1 gram sample of plutonium-239 to decay to 0.1 grams? Okay, these half-life problems, if you don't memorize that formula, they're like 2-part problems. Okay, so the first part is always to find the rate. So we're finding the rate of decay. It's going to be a negative number because we're decaying. So we start out with our A equals P e to the RT. And we use that half-life. So we say, okay, this amount that we start with is decaying to half of what we have in how many years? 24,110 years. Okay, so if I had 1 gram of this plutonium, it's becoming how much after 24,110 years? So if I start with 1 gram, it's becoming 0.5 grams. Do you guys see that? So after that certain amount of years. So we're starting out with 1 gram and it's becoming 0.5 grams. After a certain amount of time, the lovely 24,110 years. That's how long it's taking. The only variable there is r. E is not a variable, right? E is a number. So we are then able to solve for r. So we divide by 1, right? Dividing by 1 is still just 0.5. So I have 0.5 is equal to e to the 24,110 r. How do you think I'm going to solve for r? Yeah, you could switch forms. You could take the natural log of both sides, right? So I'm going to get the natural log of 0.5 equals natural log of e, which cancels, of the 24,110 r. So this part's gone. 24,110 is not hanging in space. It's been dropped. It was pulled to the front when we took the logarithm. So our r ends up being natural log of 0.5 divided by 24,110. Look up here at the thing in the box. R equals natural log of 1/2, natural log of 0.5, divided by the half-life, 24,110. So you can skip these steps if you know that formula. Okay, if not a big deal. You can get it from the one we already know. So let's find an approximation for this. So go ahead and get your calculator out and do this approximation. Eric, I'm bummed because I used to have 2 calculators, but I don't know what happened to my other calculator. So someone has stolen it. Someone took my calculator. So I have natural log of 0.5. Here, I'll do it on the Wabbit thing over here. I know, someone. I will not tell you who, but one of my calculators of my tutoring student, I was like, she goes, I don't even know where I got this calculator. And her mom had put a label on the back that said her name. And I was like, oh, it looks like a calculator that I used to have. And she was like, well, let's see if there's like a name on it or anything. She pulls off the label and underneath it says Mrs. Cox. Her mom put a label over my name. And she took my calculator. Kills me. But I got it back. I know. Hilarious, isn't it? Okay, so anyway, Eric, you can use this one. So here's what we're going to do. So I'm putting in the natural log of 0.5. I'm dividing by that 24,110. And I get a crazy number. Do you guys see that? That's scientific notation. That is negative 2.87 something times 10 to the negative 5th. Do you guys see that? Okay, so let's write that rate down. So it's negative 2.8, was it 75 times 10 to the negative 5th? Okay. And then I go on to part 2. And the second part of the problem says, well, how long does it take for 1 gram to decay to how much? 1 gram to go to 0.1 grams. That's the second part of the problem. So the first part only uses the half-life. So now we're saying, okay, well, I'm starting out with 1 gram and I'm decaying to 0.1 grams. And my rate is still that negative 2.875 times 10 to the negative 5th. Do you want to write that every single time? I don't want to write that every single time. So your calculator has this handy thing where you can store a value. Have we done this before? I think we have. All of them, yeah.
Oh, that's the one.
Oh, that's the one, yeah. That said Mrs. Cox underneath it, yeah. All right, so we're going to hit STOW. Do you guys see STOW? It stands for store. And we want to store that value as something. So I'm going to store it as A. So I'm going to do alpha A, and I have that number. Now, anytime I want to use that number, I just put in alpha A. So if I wanted to find 1 plus alpha A, I would do 1 plus alpha A, and it would give me 1 plus alpha A. Okay? Yep, so we store it as A. So what we're going to do is in this equation, we don't want to write that crazy rate all the time. So I kind of write an A and I circle it, and then I put an A and I circle it. So I know that's a stored value. And we're finding how long it takes, so we're finding T. And then we solve this out. So I divide by the 1, so I still have 0.1, equals e to the A times T. How do I solve for T? What's the next step? Natural log of both sides, so natural log of 0.1 equals natural log of e, A times T, natural log of e cancels. So I end up getting natural log of 0.1 divided by my A value. That's going to be my T. So I go back to my calculator and I do natural log of 0.1 and I divide by alpha A. So when I do that, my answer is 80,000, so 80,091.686. What did I say, 696? 686, thank you. So it takes a little bit more than 80,000 years for it to decay to 0.1 grams. Does that make sense? Do you guys get it? Okay, so I know those are time consuming and it's time to go. So there's other examples. We can finish this tomorrow, but oh, Kyle, it was about you too.
Wait, could you go back to the answer?
Yeah, I'll go back there. All right, so I'm going to give you your homework. You guys can do your homework. We didn't get to bingo, so hold on to your bingo. We'll play bingo so you guys have the chance for a bonus point. And then a couple of those bingo problems, I didn't realize they used E, so I really should have assigned it after 10.5. So you can go back. It says Kyle has $5,000 in his checking account, which earns 3.5% interest compounded continuously. Okay, so like I said before, we probably don't do things compounded continuously in the banking world, but we're going to do it in these examples. So continuously, just underline it. Every time you see that, that's the A equals PE to the RT formula. So it says, what is his total amount? What is the total amount of his investment after 3 years? So we're finding the amount after 3 years. He put in $5,000. We have E instead of the 1 plus R over N stuff. So we have E to the R, which is 0.035 T. And T is going to be 3 in this case. So be careful with putting that into your calculator, because if you make a mistake with parentheses, so as you guys can see how I put like 0.035 times 3, your calculator will do that according to the order of operations. So if I put that in 5,000 E, so E is a button that's along the left-hand side. It's where the natural log is. So we do second natural log. And then I put in 0.035. And then if I ended the parenthesis and put 3, that would be wrong, okay? It would give me too much. It gives me that answer, 21,000 something. So what I should really do, notice I'm doing second enter, it pulls up the last thing I did, is I shouldn't do like that, I should do times like that. So 0.035 times 3, all of that in parentheses, so I get this number. Okay, so I get 14,288. Oh, I did 0.35, that's funny. 0.035, sorry. I was like, that still seems big. I made the mistake that I was just telling you my students make all the time. So 5,553.55 is the amount after 3 years. Okay, so the question is, how long does it take for the investment to double? Okay, so if we're trying to find how long it takes for the investment to double, how much did I start with? I started with 5,000. What am I going to put in for my new amount? 10,000. Thank you. So I'm going to put 0.035. I'm finding the time, so T is what I don't know, and I want it to equal $10,000. So I don't do 10,000 of T or anything. That's my amount after T years, 10,000. So when I divide by 5,000 on both sides, what do I get? Oops, 5,000. I get not 2,000, 2, right? What if I said, how long does it take for his investment to triple? What number would I get over there? 3, quadruple, 4, right? Does that make sense? So it actually didn't matter what I start with. I mean, Kyle could have started with $18 trillion. How long will it take for him to double his investment? I would put $36 trillion in the other side, right? And when I divide it out, I'd still get 2. Okay, so it doesn't matter what you start with. So a lot of times, like on the test, I'm kind of mean about it. Sometimes I don't tell you what you start with. So in that case, we would put like P, and this side would be 2P. So I could do that, right? It doesn't matter what we start with. So now we find our answer. So we're going to take the natural log of both sides. So I'm going to do natural log of 2 equals natural log of e to the 0.035t. And the natural log and e cancel. So I have my 0.035t equals natural log of 2. So I divide by 0.035. So I get t equals natural log of 2 over 0.035. Okay, so what is that? Did you guys find that? What was it, Jacob? 804. So around 20 years. So a little bit less than 20 years. Is that years, I'm guessing? Okay, so last one. One more of these like half-life problems. So it says a paleontologist uncovers a fossil of what he believes to be a woolly mammoth in California. He analyzes the fossil and concludes that the specimen contains 15% of its original carbon-14. Carbon-14 has a half-life of 5,730 years. Use carbon-14 dating to determine the age of the fossil. Okay? So, if we're doing this, then we're going to first start with our first part, which is just finding R. So the only thing we use for this is this 5,730 years. So we have our amount equals PE to the RT. We start out with whatever we started with, P. It doesn't matter what it was. And I have half of that on the other side. So I'm writing half P over here. So notice in the problem, it doesn't even say how much carbon-14 there is. I don't have like 100 milligrams or anything like that. Do you guys understand that? So I have half P equals P E to the R times 5730. So it seems like we have too many variables because we have R and we have P, and then E looks like a variable, but it's not, right? It's a number. So it looks like we have too much, but notice when we divide by P on both sides, what happens? Yeah, those P's go away. Kind of like that last example we just did when we doubled the investment, tripled the investment. The amount ended up not mattering. We just got 2 or 3 or whatever. So I'm going to have 1/2 equals E to the 5730 R. So I take the natural log, take the natural log. So I get natural log of 1/2 equals 5730 R. So my R is equal to the natural log of 1/2 divided by 5,730. So we've done a couple of these problems now. Do you guys see where the rate comes from? It's always from the half-life, which is giving us 1/2 on the left side. So we eventually take the natural log of 1/2, right? And then we divide by that half-life. So if you notice, I gave you that formula. It was here in your notes. So if you just know that formula, you can skip half this problem. You can have the problem with half-lives, right? So we have the second part of this problem. That's what we're going to do now, and we're going to use that rate. So let's figure out what this rate is on our calculator. Did you guys get it? You're going to need to do this in this little activity that we do later, so let's all do this right now so you don't have to do it in the activity. So we get natural log of 1/2 or 0.5, and we're dividing by 5,730. So we do get negative 1.2096 something. So we'll say negative 1.21, let's say, times 10 to the what? Negative 4. That's our rate. So that's the rate of decay for carbon-14 always. It's always that because it always has that half-life. So now our second part. The problem said that the specimen contains 15% of its original carbon-14. So if I start with my Pert equation, so I have A equals PE to the RT. Under P and A, P, I'm putting P. A, I put, yeah, 15% of what I started with, 0.15p. E, and then I have my R, which I'm going to save. I'm going to store that, so I'm going to hit store as alpha A, so I have it. So I'm going to write a little A there, so I know I stored it, and I'm going to put that little A over here, times T. Okay, this is pretty hard. Do you guys understand this? It's a tough question. And then we divide by P, and those P's go away, so the P didn't matter. So I get 0.15 equals E to the A times T. Natural log of both sides, natural log of 0.15 equals A times T. So we take that natural log of 0.15, and if you did it, and you were like, oh no, I forgot to divide by that answer, that's why we've stored that answer. So now we do divided by alpha A. But some of your calculators, you can go up and grab the things, right? This one's a good one to store. So we end up getting 15,682 years old. Okay, so I don't know if that's a woolly mammoth or not. I don't know when woolly mammoths were around. Do we know? I should probably look up when woolly mammoths were around. But yeah, so he could determine whether or not that was true, if it was a woolly mammoth or not. Make sense? Okay, so we're going to stop.